Let's try to squeeze one reduction into the last few minutes, okay? It's spelled out in detail on the slides, but let me give you the gist of it. A more typical example of a reduction, the one that we'll look at, relates this problem 3-SAT, which is a Boolean formula where everything looks like this. It's a big AND, and what is in the AND parts is an OR of variables or negated variables. So all the inputs look like this, plus each of these clauses have at most 3 literals in them. So literal is this thing, a variable or the negation of a variable, and a clause is the OR of 3 such things, of 3 literals. And you can show that this is NP complete. Some of you will look at that. And the second problem that we reduce to is vertex cover. That's what I asked about initially. Vertex cover, on the example, you're given a graph and you try to select some vertices so that all the edges in the graph have one endpoint selected. So you could always pick all the vertices and satisfy this, but the goal is to find a small subset of the vertices. And the decision version has a threshold, so you're not allowed to pick more than k vertices, and you want to satisfy the condition that every edge has one endpoint selected. For example, here, a smallest vertex cover uses 3 vertices. Then all these edges have at least one endpoint selected. It's fine to have both endpoints selected. And you cannot do it with just 2 vertices, in this case by just trying all options. And the full proof should show that vertex cover is NP complete. That consists of 2 parts, showing that it is in NP and that it is NP hard. And let's only sketch the NP hard part. The intuition that you should follow, and that's what you do in your reductions too, you take the new problem, vertex cover, and suppose that that is solvable. And now you take an instance of the old problem that's known to be NP hard, and you cast it in the language of this new problem. So we express a 3-SAT instance, a formula, as a graph, so that the vertex cover of this graph says something about whether or not this formula can be satisfied. Okay, and here's the formal construction. I only have time for the example. Here's a formula. It has these clauses. For each clause, you make a little triangle, and it's connected by these blue edges. And the vertices are labeled by the literals in the clause. That by itself wouldn't be interesting, but you add green edges between every 2 literals in different clauses that contradict each other. So here I have x1 and not x1. I cannot have both at the same time, put an edge between them. And you do this for all pairs of literals. If they are a variable and the negation of the same variable, put an edge between them in green. And then the key observation is that if that formula is satisfiable, it means there's a way to set the variables so that in each of those cases, one of the 3 at least is true. And then you can pick the true thing and make that not part of the vertex cover, but take all the other vertices. So here you would read off an assignment of the variables that satisfies the formula by setting x1 to false, x3 to false, x1 to false again, okay, and x4 to true, and that should satisfy this formula. Now the thing is, if there's a way to pick from each triangle 2 vertices such that all the green edges are covered, then you exactly satisfy the formula, and that's an if and only if. It goes both ways. The full proof in all details is spelled out on the slides. So if you haven't seen this example before, you can read it there. I hope it's actually clear enough even without my voiceover.